evening to all of you. So today this is the week 6 of the problem solving session to the Introduction to Fluid Mechanics course taken by Professor Suman Chakraborty. So we will wait for a few minutes for students to join, and then we will continue with the problems. So today we will basically start with hello, am I audible? Am I audible, Priyanka? Okay, thank you. So because of some unforeseen circumstances, I couldn't take the last week's problem solving session. So I will try to combine the concepts of both the weeks today. So it is a very conceptual session, but as well as concise. So the session would not last too long for today, as it seems. But still, I hope you have attended both the lectures and the other two problem solving sessions for the past week, and hope you are capable. You will be able to answer some of the questions that have been discussed. So I think that's fine. So you may ask if you have any doubts regarding both week 5 and week 6 concepts. We can discuss that. Because I would like to wait for a few minutes for other students to also join. So if you have any doubts, you can please ask. Otherwise, we can just discuss the problems, then just finish the session. Do you have any doubts from the week 5 and the week 6 concepts? Okay, thank you. So I will wait for 2 more minutes, then we can just go through the concepts briefly and then discuss the questions, and then just finish the session, because I don't think there's too much involving questions for these 2 weeks, but still we need to discuss as per the curriculum. So we will wait for 2 minutes. Since no other students are joining, I think we can start. Since only one student is there, then we can just have some discussions. So Priyanka, you can unmute yourself to answer. I just wanted to ask you regarding the difference between the Lagrangian and Eulerian approach. So could you please briefly explain me about that?
Hello, sir.
Yeah. Yes.
So regarding Lagrangian approach, it is the particle approach,
Okay.
and whereas Eulerian approach, it considers a region.
Okay. So
So I think we can connect it to the continuum approach which we discussed on week 1.
no.
Can we?
No, actually, it's not like that. If you don't mind, I'm having a bit technical issue from my side. I will just leave and join again if you don't mind, okay?
Yes, sir.
Yes, sir. I'm really sorry because I'm not able to get your noise in the recording, so I need to uh, leave and join again. So please don't mind, okay? I'll just join now. Leave and join. You can stay in the meeting.
Yes, sir.
Yeah. Okay, am I audible?
Yes, sir.
Okay, the problem still persists, but I hope it will fine. It's fine, no problem. Yeah. So the thing is, actually, it's not that we were trying to connect the Lagrangian or the Euler, the Lagrangian and Euler approach with the continuum hypothesis. Actually, the continuum hypothesis is the basic requirement for the validity of the mathematical formulations that we do to solve fluid mechanics problems, right? Eventually, when we will reach the dynamics of the even from the kinetics part itself, when you reach the mathematical formulation of fluid flow, the very basic, like the basic fundamental or the validity of these governing equations lies in the continuity of the flow domain. So if the continuum hypothesis is not valid, then we cannot implement these governing equations, right? So the continuum hypothesis is important in that point of view, but the Lagrangian and Euler approach are two different approaches that are used to solve fluid mechanic problems and are not directly related to continuum hypothesis, but the existence of the continuum hypothesis is the precursor to or the requirement or the fundamental requirement before solving any fluid mechanics problems. Okay, I guess I'm clear up to this part.
So just one doubt.
Okay.
Regarding the Lagrangian approach, like
Okay.
while discussing about continuum mechanics,
Yes.
that hypothesis,
Yeah.
uh, uh, like we we restricted ourselves to a certain number, 0.1, like no slip and slip region. In that, it was mentioned that if it comes under continuum hypothesis, then we can take as a region. Like we can take it as a continuity.
Wait, which one? I couldn't get your question. Could you please repeat? Priyanka?
Sir,
Yeah.
yes, sir. Regarding continuum hypothesis,
Okay.
We like we restrict ourselves to Knudsen number.
Okay. Yeah.
So like if Knudsen number is between 0.01 to like point like 0.01 to 0.1, we said that we can take continuum hypothesis.
Okay. Yes.
We can take the fluid as a continuous medium. So doesn't it mean that we are taking Eulerian approach there?
No, 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 no. The thing is that the very definition of fluid particle doesn't reach to the molecular level of the fluid flow. Okay, the very definition of fluid particle means that it is a collection of fluid molecules that have the same identity and the same velocity or the fluid flow characteristics in that point of view. Okay, it does not mean a fluid particle. It means that it's a fluid molecule. It doesn't mean that. We do not talk up to the fluid molecule level. And the Knudsen number comes in a picture when we talk about the mean free path. That is how long a fluid molecule will travel before it collides with another fluid molecule. That mean free path and the ratio of that mean free path to the characteristic length scale that we are considering is known as the Knudsen number. So if that is in the certain range, then we can say that the continuum hypothesis is valid. It is and only then we can apply our fluid flow equations and the Navier equation. Then only then we can apply those governing equations. Otherwise, we cannot apply, because if the fluid domain is not continuous, then there's no point of having differentials or functions defined in the domain. So that's first part. Okay. And regarding the Eulerian approach and Lagrangian approach, I would say it is not directly related to the continuum hypothesis, but the continuum hypothesis, the validity of the continuum hypothesis is a precursor to the validity of these two approaches. This is the second point. Okay, I guess I'm clear. And now I would like to make you clearer or clear regarding this concept. Now I'd like to individually ask, since I guess both the definition of both the approaches are already there on the screen. So what do you understand by Lagrangian approach? Just the definition. Don't go to the continuum hypothesis now. Just by definition, what do you mean by Lagrangian approach?
We study each and every particle present in the domain.
Okay, right. So say this is our flow domain. Say this is our flow domain. Say this is the domain that you have considered, and there can be n number of particles in the flow domain. Okay, and particles does not imply fluid molecule. I'm again and again saying fluid particle does not imply fluid molecule. It's actually collection of fluid molecules that have the same identity and the same flow characteristics. Okay, that is the basic definition of fluid particle. I guess Professor Chakraborty has discussed that in the lectures. So from that only I'm saying, say there are n number of particles in this fluid domain. Okay, so what Lagrangian approach actually does is to understand the flow behavior within this domain. What they do is they study the behavior of each and every particle within the domain. Okay, say if I zoom in, say this is particle 1, this is particle 2, and this is particle 3. Okay, 1 2 only 3, say we're only considering the 3 particles. Okay, so say the flow is the flow is flowing from left to right. It has some velocity and it is flowing from left to right. Then what, because of this confinement, first because of the inertia of the flow, it will have some initial momentum, right? And secondly, okay, did you say anything? Okay, and secondly, because of confinement, the boundaries of the wall, the flow will interact with the confinement, the boundaries of this. I'm sorry again, I should simplify it by, because this is not at all possible if it is a close confinement. So yeah, let's erase this confinement. Okay, say this is a flow between two parallel channels, and these particles are flowing with some initial momentum. Okay, and then what do they interact with the walls and form a boundary layer, which we'll eventually discuss in the dynamics of the fluid flow. Okay, they form a boundary layer. Okay, so what will happen, what we do is in the Lagrangian approach, we try to calculate the velocity of the particles at each and every point. Okay, how will we do that? Say the velocity of a particle at point 1 at a particular instant would be given by u is equal to dx by dt, right? Then v would be dy by dt, and w would be dz by dt, right? So then what we do is, if we know the velocity field, say, then what we do, we track the trajectory of the particles, like how the particles will move for with time, how the particles will move in this confinement with time. Okay, so how to do that? Basically, to get xt, say, then we just integrate this differential equation. Then we get xt is equal to integration of u dt, because we don't know if u is constant. So say we use a function of time, the integral of u of u dt plus some constant. Okay, so this is the way we track the position of the particle with time. Similarly, we calculate the y coordinate and the z coordinate. So like this, if we know the velocity of the particle at each point, then we get the trajectory of the particle within the confinement. Okay, so this is basically known as a Lagrangian approach. You follow the position of each and every particle, then obtain the velocity field and the velocity field by solving the governing equations and obtain its trajectory. Okay, but now if we is that clear?
Yes, sir.
Okay, but as you can see, for 3 particles itself, this is a very cumbersome job. Okay, it's a very challenging job to only track 3 particles, and in general, in our basic fluid flow problems, when we try to find a particle trajectories, we only deal with 2 to 3 particles to get just the general behavior of the particles within the confinement. We try to track only 2 to 3 particles. We don't go beyond that because it's very difficult even for the highly advanced computers at the present time. So it's not at all possible to know the flow behavior for each and every particle within the confinement. Okay, so that's not possible. It's a very it gives a more clearer picture of the fluid flow behavior compared to the Eulerian approach, but as we know, like we don't get like don't actually get that we don't actually receive or get the outcome is not equal to what we put in, what efforts we put in for obtaining the results. Okay, so the efforts put in to obtain the outcome is much more greater than the outcome itself, so it's of no use. That's why the mathematicians came up with the Euler approach. Here what we do is then okay, let me hear it from you only. So what's an Euler approach then?
Eulerian approaches, as sir explained in the video, that
Yeah,
in a particular region we sit with the camera and capture.
yeah, absolutely correct. So uh,
We don't go for particle 1, 2, 3, like we go for Lagrangian.
yeah, that's absolutely correct. Yeah, because as Professor Chakraborty explained, it basically means that instead of following each and every particle, what we do now is we consider this region as a black box. Okay, so say we consider this region as a black box. So we don't care at all care what's happening within this region. What we need now is we need the velocity of the particle at point 1. Say we need the velocity of particle at point 1 and at point 2. And if we know the velocity field at these 2 points, then we can basically get the net force that is acting in this region. Okay, acting in this region. So at last that's all that we need, right? So once you know the velocity field at these two ends, say at these 2 points, then we can obtain the uh, by applying the governing equation, basically the Navier-Stokes equation, we can find the net force acting in this flow domain. So that's all that we need. So we don't at all care what's happening within the flow domain. So we basically treat it as a black box. So we don't know what's happening within, but once we know the velocity field in these 2 points, we can get the net force and acting in this control volume or this black box control volume. Basically we'll know control volume when we solve other fluid flow problems. So we know that, and then subsequently we can find the pressure gradient and the pressure by solving the Navier-Stokes equation. So this is the difference between the Eulerian and Lagrangian approach. But you may think that okay, sorry. So just to brief you about the later part of the course, just as an introduction, like you will even have you heard about the term RTT, the Reynolds transport theorem, like by chance, or have you read about it?
Yes, sir.
Okay, so can you tell its importance?
We use it to connect between control mass and control volume approach.
Okay, yes, you're absolutely correct. But why do we need it? Like, why do we need it? Why did they come up with such an approach?
Due to difficulty in calculations.
Yeah.
I'm guessing it.
Yeah, it's correct. See, the thing is that the all the fluid flow problems in fluid mechanics basically deal with 3 equations. First is the continuity equation, then the momentum equation, then the Navier-Stokes equation, and then finally the energy equation. So the thing is that these equations are based upon the works of the scientists, that have done that have worked in the domain of mechanics. So deriving their works, deriving from their works only, we have developed the scientists have developed the domain of fluid mechanics. Okay, but the issue was that these governing equations that they have derived were initially for a control mass system, right? So, and again, as I already told you, control mass system basically implies to a Lagrangian approach. The mass of the system is conserved in that sense. So since these equations were derived only for control mass systems, as you rightly mentioned, it was very difficult for the scientists to go through those approaches and then obtain the solution. It was nearly impossible and still impossible for the most highly advanced computers. So that's what really impossible, or in a correct word should be infeasible. It was not feasible, and that's why to connect this Eulerian approach with the Lagrangian approach, they have developed the RTT, right? The Reynolds transport theorem. And eventually we'll get to know how they have derived it and what is the real importance of the Eulerian approach in fluid mechanics. And also, if you go for higher studies and research, you will also get to know how sometimes Lagrangian approach gives a clearer or better understanding for fluid flow problems compared to Eulerian approach. See, Lagrangian approach is not a vague approach. Okay, it's very good, or to say, it's a very accurate approach and gives a much more clearer idea than the Eulerian approach. But for most of our fluid flow problems, we can only deal with the net force that acts because of the fluid flow, right? That is what we actually need for any turbo machineries that we deal in our day-to-day life, is the net force that really drives our problems, right? Is the really the main source or the main solution to our problems, the net force that acts in these fluid machineries. So that's why we only need the Eulerian approach for most of our problems. But for higher research problems, you will eventually know that how Lagrangian approach could help to get a much more clearer understanding of the more intricate flow behavior in basic fluid flow problems. So that's why we need both the approaches, but we also need to know when to apply which approach, so that our life is not trapped in solving fluid flow problems that are absolutely infeasible. So that's why we need to know these two approaches, also their differences, their advantages and disadvantages as well. So I think it was clear.
Yes, sir.
Okay, thank you. So again I guess sir have discussed about streamlines, streak lines and path lines. So can you please tell the basic definitions of them? It's very simple, just skip past it as fast as possible.
So for streamline, it's like the imaginary line
Yeah.
that gives the velocity at particular time.
Okay. Velocity. Okay. Right. That's fine.
Then coming to streak line and path line, both streak line and like path line are similar, but the difference is that in path line it is the same particle, locus
Okay.
of the same particle.
Okay.
Whereas in streak line, we fix a point and the number of particles the locus of the number of particles passing through that point, that gives the streak line.
Yeah, you're absolutely correct. So you have defined it all the three definitions correctly. So thank you. But so let me ask you one question again. I guess Professor Chakraborty also discussed that in the class. So that die problem, yeah, that we use to visualize the fluid flow, what actually it is? Is it the streamline, the streak line, or the path line? That we insert a die in a fluid flow, then we try to visualize the flow field of the fluid particles in that flow. So is that the die that the die that follows, the path the die follows, is that a streak line, a path line, or a streamline?
So during steady flow, it will be same.
Yeah, that's same, but
And
usually it's not
yes, sir.
same. Yeah, usually it's not same. Usually it's not steady. So say it's an unsteady problem, and we are putting a die in a flow and trying to try to see the fluid flow, or try to visualize the fluid flow. So what actually is that, fundamentally or by definition, what actually it is?
Streak line.
Yeah. Yes, you are correct. I hope you didn't guess it, but you are sure about it. So yeah, it is actually streak line. Okay, so what basically happens is that when we insert a die, say we insert a die in the fluid flow, so this is the fluid flow and we're inserting a die. So what happens is that different particles are being inserted because of the die. So different particles will follow a trajectory. Okay, will have different trajectory, but what we basically visualize is the locus of all the particles that pass through a particular point. Okay, that's what we actually visualize. So that's why this is actually a streak line. We say that, or we even assume that as a streamline, but fundamentally by definition it's a streak line. But again, I guess Professor Chakraborty again showed you some problems of highly viscous fluid flows, where he shows how the dyes help in visualizing a fluid flow around a 2D cylinder, how they help to visualize the flow around 2D cylinder. So in those fluid flows, we can, by certain assumption, we can assume the flow to be steady, and because of that we can aptly say that both all the three lines, that is the for steady flow, that the streak lines, the streak line, the streamlines, and the path lines are identical. So basically, what we visualize is by certain assumptions, the streak lines can be assumed to be as streamlines, and thus the fundamental characteristics of the streamlines could be uh, visualized upon by the help of streak lines. Okay, so I guess it's clear.
Yes, sir.
Okay, thank you. So again, then we see about the acceleration of fluid flow. I guess the formula is clear. So is there any doubt in this regard? So if you have any doubt, you can ask, or like we can just skip it, so we can discuss the problems. And yes.
No, sir, no doubts.
Okay, thank you. I guess it was clear. So can you tell me the difference between these two derivatives, capital D by dt and this partial derivative del by del t? What's the difference between these two?
The capital D by dt was the total derivative.
Okay.
Whereas the small, that del by del t is the partial derivative.
Okay. So yeah, that too I know, that is visible here. But what's the basic difference, or if I try to ask in a much clearer, in a much more accurate way, so why does this term come into picture while defining a total derivative? Why does this term come into picture in fluid flow problems? Like, could you tell, like, why does this term come into picture?
Because no, like the change in the property is not just with respect to time, but also with respect to the position. Because here we are when fluid flows, there will be deformation also.
Okay. Oh, so you have dealt with the next topic. That's fine. Yeah, deformation. Okay. Yeah, that's fine. Could you tell an example where this term like is really significant, or the implication of this term comes into picture, of how the fluid velocity may change with position even when the flow is steady?
Sir, if the shape of the like where the fluid is like container,
Okay.
I'm not sure about the exact term. If it is not uniform shape, if it is different shape, like converging, diverging.
Oh, yeah. Say this like this, right? Converging, diverging nozzles.
Yes.
Okay. Yeah, thank you. I just wanted to know. I asked because I wanted to know that whether you're conceptually clear. So you're conceptually clear. That's fine. So even though the flow is steady, the flow velocity will change because of the change in this area, and that can basically be understood by the continuity equation. So that's fine. Yeah. Thank you. Again, since you have discussed about deformation, so I guess there should be no doubt again in this regard. So there's linear deformation, then there's volumetric deformation. So is there any doubt in this regard? Deformation fluid elements, linear deformation,
Yes,
at least.
sir.
Okay. Okay. Let's then I guess again we have discussed about angular deformation. So could you please tell me about the difference between this angular and linear deformation?
So from the word, like we can say that one is linear and one is angular. Like
Yeah, that is true, but a bit more. Okay, linear I can understand.
okay, so
Yeah.
linear deformation means like in angular the shape will change. In linear the volume will change.
Mm, ah, maybe it is correct, but I don't know. By my
Is it
fundamental,
correct?
that I don't know. By my fundamental understanding, it is not the actual definition. Like in basically like linear deformation, what does it really mean? Say a rod is subject to a linear deformation, what would happen?
Its length will change.
Yeah, it will elongate, right? So that basically
Yes.
means linear deformation. And if you then consider the lateral deformation, then it will again have some lateral deformation. That's fine. But what then? What then does the term then angular deformation mean? In your definition, you have
So rotation, can I say rotation? Because in the example, like if we took a square, it became like a rhombus.
yeah. See, rotation. When you say that, use the term rotation, it can imply that the square that you initially assumed itself is rotating about an axis. Then it's not deforming, right? If you assume a square and assume that, say, this is an axis coming out of the this is an axis coming out of the paper, of this paper. So you can assume that this square is rotating about this axis, say zz. This is also rotation, but the fluid is not deform. The fluid element is not deforming in this case. So could that, then can we say it as an angular deformation?
With respect to the reference, it has changed the position.
So it has changed the position, but the identity of the fluid element has remained the same, right? The shape has remained the same. There is no deformation at all in this case, even though it is rotating, but it is no deformation. You have said the term that the fluid element had changed its shape from a square initially to a rhombus, right?
Yes, sir.
Yes. So say that basically you can say that the shape of the fluid element in angular deformation changes with respect to its initial axis, which were initially perpendicular. Like the size of the fluid element, if it was perpendicular to each other, they deform according in a way that they are not perpendicular anymore, but has taken some angular deformation with respect to the initial axis. Is that understood?
Yes, sir. So the previous question which you asked, that if it is just rotated, then it is not angular deformation.
Yes, it's not angular deformation.
Okay, sir. Okay, sir. Okay? So we should take the reference of the two lines.
Yes, we should take reference on the two initial perpendicular axes which define the edges of the fluid element. It is respect to that only the fluid element has deformed, right?
Yes, sir.
Yeah, so that's important. Yeah. So again, I guess I don't want to repeat how they have how sir have derived to these equations. I guess sir has elaborately discussed in the lectures. If you have any doubt, then you can just revisit the lectures and it will be much clearer. Again, this concept will also be clearer when you revisit the lectures. So I guess this is fine. So yeah, I guess that's all. Again, angular velocity. So any doubt in this regard? Angular velocity and vorticity.
No, sir.
Okay, now now I have reached an important concept, a very powerful concept in the fluid mechanics domain. So stream function. So I don't want to know the definition of stream function because it's a very mathematical approach for defining the fluid velocities in terms of a in terms of a function. But what is the precursor of defining a stream function? Like, what are the two important parameters that are required to be satisfied to define a stream function? Could you please say?
The flow should be 2D.
Okay.
And it should be incompressible.
Yeah. Thank you. It's you should be very clear while applying stream functions in a fluid flow problem that it should be 2D and incompressible. Okay. And it can be 3D also, but in a sense that it is axisymmetric. Do you understand what's axisymmetric flow?
It is symmetrical. Is it similar to symmetrical, sir?
Symmetrical in the sense that symmetrical term doesn't really appreciate the importance of the word axis. Like, it should be symmetrical about an axis. So basically I mean to say there is a flow in a cylinder, right? Say there is a flow in a cylinder. uh, I'm sorry again. Say there is a flow in a cylinder, and say this is the axis through the center of the cylinder. So axisymmetric flow basically means that the flow behavior with respect to the axis for any theta, say if this is the circle, the position of the top face of the cylinder, and if we define, yeah, so this would be theta, right? So this is a theta. So axisymmetric flow basically means that there is no variation of fluid properties with respect to theta in within the cylinder. Okay, such kind of flows are known as axisymmetric, and you will deal with such flows when we solve the when we discuss the next topic, that is dynamics of the fluid flow, and try to solve the some exact solution of Navier-Stokes equation. We'll deal with such assumptions and how assuming the flow to be axisymmetric helps in simplifying the problem, uh, or cancelling some extra terms in the governing equations. You will encounter that. So this basically means axisymmetric. And here also, if the flow is axisymmetric, the flow basically depends on the z coordinate and the radial coordinate, right? The r direction. The flow only depends on these two coordinates, and it's independent of theta. So in such kind of flows also we can apply stream functions. Okay. Even though the flow is essentially 3D, but since it's axisymmetric and the flow basically depends on two coordinates, that is the r and the z axis. So in such kind of flows we can still apply the stream functions. Okay, so I guess it's clear, and how it is defined also it's clear. So yeah, so do you know about velocity potential then? What's velocity potential?
It is defined for irrotational flows.
Okay, so how it is defined? Say there is three velocity, say for a Cartesian coordinate system there are three velocities, u, v and w. How do you define u, v and w in terms of velocity potential function?
Velocity potential taken as phi. For u it is dou phi by dou x.
Okay.
For v it is dou phi by dou y.
Okay.
And w it is dou phi by dou z.
So is it defined for 3D systems, or is it also confined to only 2D fluid flow problems?
No sir, here there is no such restriction.
Okay, yeah, that only I wanted to clear. Yeah, it is right. So there's no such restriction of 2D flows in terms of defining velocity potential. The only precursor is that the flow should be irrotational. So yeah, I guess that's fine. So now we can straightly discuss the questions, and it's very simple. I guess you already discussed it in the different sessions. So, but still, since I missed it, it's my duty to discuss it again. So yeah, for the first question, a flow is said to be uniform when, just by the definition, what would be correct? Please see the options and just tell the answer. It's very simple. Uniform flow.
So, please, the second option.
Okay, let me read. The flow velocities and fluid properties do not change from point to point in the flow field at any instant of time. Okay, do not change from point to point, remain constant with respect to both spaces. Yeah, it is correct. Actually, C is also correct, I guess. But the funny part is both imply the same meaning. Do not change from point to point in the flow field. Yeah, both are correct because both imply the same thing. No, let me just check. Okay, sorry. uh, any instant of time. Okay, respect to both space and time. Okay, I'm sorry, sorry. Both space and time is not possible. Yeah, it's B. Okay, I'm sorry. It's B, right? Sorry, sorry. It's B. Okay. So, second question again. A flow is said to be steady when?
Sir, option A.
Okay. Flow velocities and fluid do not change with time at any point in the flow field. Okay. So yeah, like in the previous question, I was saying the wrong answer. So if I'm wrong, please correct me. Okay. Like I may be wrong sometimes also. So please correct me. So yeah. Again, a path line. That's the definition of path line. Yes.
Sir, C.
Yeah, it's correct. The trajectory of a fluid particle of fixed identity. Yeah. For streak line, they're basically asking the definitions. A streak line at any instant is,
Sir, B, sir.
yeah. And then 5. A streamline at any instant of time is a line. Okay. Streamline.
Sir, D, sir.
Yeah, it's correct. And question number 6. Okay. Uh, which among the following statements is or are correct for a steady uniform flow? For both a steady and uniform flow.
Sir,
Yeah.
sir, all the options are correct.
Let me check. I don't know. Why do you say so?
So with respect to steady, the local, the first term, it will be 0.
Okay.
And since it is uniform, then with respect to position also, it will not change. So it will be 0.
Okay. Then
So the
basically,
material,
this will be 0, right?
yes.
And streamline still and path identical. Yes. So yeah, all options are correct. Wow, nice. Okay. Then question number 7. Which among the following statements is or are correct for an unsteady uniform flow field?
So B.
Okay, similar question, but they have removed the steadiness of the flow field. So uniform is just uniform. So convective acceleration would be 0. Temperature will be non-zero. Then this basically means this will be non-zero. And yeah, right, correct. Question number 8. Which among the following statements is or are correct for a steady non-uniform flow?
So A and D.
A and D. The temporal
Yes, sir.
acceleration of any fluid element is 0. Yeah, because it is steady. So steady and non-uniform. Then this will be non-zero. It's not correct. Then this would be non-zero because this term is non-zero. Yeah, and because it is steady, then this will be identical. Yeah, both A and D are correct. Okay, the equation of a streamline for two-dimensional velocity field V is equal to given by ui cap plus vj where u and v are functions of x and y. So what is the equation of streamline for a 2D flow field given by this velocity field?
So C.
What? C.
C, sir.
C.
Third option.
Okay. Okay. Since we have discussing our streamlines now, so uh, are streamlines also only valid for 2D flows, or also or else, or are they are valid for 3D flows also? Streamlines, not stream functions.
So streamlines are there for all the flows.
Okay, right. And stream function only valid for 2D incommensurable flows, right? Yes. Now I'm just asking because it's very important, because sometimes, like, even I or other or students, also even different other researchers also get confused regarding the concept of streamlines and stream functions. And funny enough, I also have learned the main difference between them only when I've listened to the lectures of Professor Chakraborty. So I just wanted to check whether the concept is clear between the concept is clear regarding the difference between streamline and stream functions. So yeah, so thank you. So it's correct. Yeah. So last question last question for the week 5 assignment. For a certain two-dimensional incommensurable flow, the velocity field is given by this x square I cap plus 2xy j cap. The streamlines of this flow are given by the family of curves. So these are the options. So which is correct? Could you please solve it and just find? So
Sir, first option. A.
first option.
Yes, sir.
Could you please check again? It's, I guess, x square I cap plus 2xy. So could you please check again your derivation, because it's not correct. Please go through it again. Maybe you'll get your mistake. A is not correct. Or if you don't get the answer, you can just do what you have written in the screen and then check the mistake. That would be again.
Sorry, sir. It would be option D.
Okay. Now you're correct. Yes, that's fine. Very simple. So I don't think I need to do it in the screen. So yeah. So again, so since we are discussing about streamlines and streamlines, I don't actually remember like whether Professor Chakraborty has discussed regarding this, but I just want to know, like, even though they are different, streamlines and stream functions, they still have what to say, a slight relation. So could you tell me, like, what is the relation between a stream function and streamline for a 2D flow? Since I defined 2D flow, for a 2D flow, what is the relation between, or is there any connection between streamlines and stream function? I don't know whether I've discussed it or not, but I just recapitulated, so I just wanted to ask.
Yes, sir.
Yeah.
It was discussed.
Okay.
That the name stream function came because of streamline, because stream function is constant along the streamline.
Okay, that's fine. But okay, right? Yes, I guess that's fine. But also, I guess sir have discussed that the to say the stream
regarding the physical significance.
What?
Is it regarding the physical significance?
Yeah, that's they mentioned correctly. That's fine. But I'm just recollecting that maybe sir have discussed that the stream function also. So the stream function for, I don't know if I'm correct or not. Just you can check it again in your notes, that the stream function between between two streamlines, like, it is equal to the mass flow rate between the two streamlines. Was it something like that? Like, I don't recall. I'm just trying to check.
Yes, sir. Flow rate per unit width.
Per unit width. Okay, that only. Just wanted to know the relation. So yeah, that's all. That's also important. It might come as some questions in some entrance exams. So just to be sure. I don't know the exact formula, but I'm just recapitulating the concept. So you can just revisit, okay? I will also revisit once. It's very important. Okay, that's fine. Again, so yeah, so week 6 also, I guess the concept that we have discussed in the class are enough to solve the week 6 problems also. So yeah, a steady two-dimensional velocity field is given by, this is wrong, field is given by V equal to A bracket xik minus yjk. So this is the velocity field. So for this we have different questions. We have 5 questions regarding this velocity field. So they have asked the rate of linear deformation of a fluid element in the x direction is given by
A. Option D, A.
Okay. Let me just write it. Linear deformation. So yeah, you are correct. That's very simple. That's right. So similarly, next question. The rate of linear deformation of the fluid element in a y direction is?
Sir, option B.
B minus A, right? So yeah, that's correct. Okay. So the rate of, I will just write the formula by that. I guess that would be correct. Okay. The rate of volumetric strain of a fluid element in this flow field is volumetric strain rate.
0.
Okay. Yes, because it will basically be del u by del x plus del v by del y. That will be equal to A plus minus A. That will be equal to 0. Okay. The rate of angular deformation of a fluid element given by this in this flow field is
Sir, 0.
Okay, because both of this term would be 0, I guess. So this will be equal to 0. Okay, yeah. Again, the angular velocity of a fluid element omega z, in this flow field is given by?
Sir, 0.
Okay, so this would be, I guess, half of del v by del x minus del u by del y. I guess I'm correct. So yeah, this would be 0. Is it,
Sir,
is it opposite?
no, sir. Regarding the above one, sir, angular deformation.
Okay.
There is no half, sir.
Yeah, that I was curious. Rightly you pointed out, but the thing is that I have also checked in different resources regarding this. So what I found is that some books they prefer using half, so that there is no terms like 2 del u by del x, 2 del u by del x in the strain rate tensor. Okay, so basically when you form the strain rate tensor for a Cartesian flow field, say for a Cartesian flow field, when you generate a for 3D Cartesian flow field, when you generate strain rate tensor, it turns out to be exx, exy, exz, eyx, eyy, eyz, ezx, EZY, EZZ. So in these cases, if we like omit the half part, what happens is that these terms along diagonal have additional factor of 2 with like before them. So just to remove this 2, some books prefer to use this half term before them. Okay, but still this is like what I have read in my masters or my currently in PhD, and we prefer to use this as our standard notation for strain rate tensors. But still I feel like you should abide by the notation that have been used for this course by Professor Chakraborty. So you may omit this part. Okay, that's fine. This will just be a removal or addition of a factor 2. Okay, sorry, a division or multiplication by a factor of 2 in the standard tensor, so that doesn't matter much. The main part is the concept of the derivative, okay, the which derivative, the along which Cartesian direction, which Cartesian coordinate which should we take the derivative of which velocity component. So this is more important, but still good, it's good that you have rightly pointed out. So I guess it's clear, it's only the notation used by different authors, okay, so that's not a big deal, but I guess you understand, okay? Is it fine?
Yes, sir.
You may use the notation used by Professor Chakraborty, okay? So that's not a big deal.
Okay, sir.
Okay, thank you. So yeah, so let's go with question number 6. Now we have the velocity field given by v equal to ay I cap plus ax j cap. I guess it's identical to what we've discussed to the previous 5 questions. The rate of linear deformation of fluid element in the x direction is
0.
right. Then along the y direction, linear deformation along y direction
0.
Yes. Then the rate of volumetric strain of a fluid element in the flow field is
0.
yeah, because both the terms are 0, so this will be 0. So next question, this is question number 8, I guess. Okay, the rate of angular deformation of fluid element EXY in this flow field is, yeah, this will be tricky if you use different notations, but still you should go by the notations used in the class. So what would that be?
Sir, 2a.
Yeah, because if I use half now it becomes a, but still since we have to go by the notation used by Professor Chakraborty, 2 is the correct option. So this would be EXY, sorry, be equal to del V by del X plus del U by del Y. Okay, so that's fine. Again, so last question. The angular velocity of fluid element omega z in the flow field is
0.
okay. So I guess these two terms both are identically 0, so this will turn out to be 0. Yeah, so that's fine. I guess that's all for this week lectures. So I just wanted to ask, like, just wanted to get a feedback from you all, but since you are only the one joining for today's session, so what is your feedback, like, since it is halfway of the problem solving session, what is your feedback about me, like about my approach in solving the problems and the problem solving sessions that I have taken so far? So what is your feedback, general feedback? Wait, yeah, you can say just fine, you can say. I will recording it, no problem, you can say.
It is very helpful, sir, because these sessions, like when we are attending the session, it is only one way. Only professor is explaining to us. But because of the sessions which you are taking, we can since it is interactive in nature, we can clear our doubts, and also the concepts which you are explaining, like few additional tips which you are giving. It is building our concepts even more.
Okay.
It is giving clarification. So it is like it is very, very helpful, sir.
Okay. Thank you so much for your kind words. And like also, like, I guess you are the only one who has attended all the sessions sincerely, all of my sessions sincerely, I guess, right?
Yes, sir.
Yeah, thank you so much. So okay, so the thing is, like, I can also you can obviously ask your doubt in the forum, but still, like, if you have any doubts even after the sessions are over, you can just mail me, okay? I will just write you my mail. You can mail me if you have any doubt regarding this fluid mechanics, because this is the topic I am working on in my PhD, so it's very important for me to be clear, like, since I will be teaching in my, obviously in near future I will also be a teacher, so it's very important to know what kind of problems students deal with, and also it will help me to grow as a teacher. So I will appreciate or encourage you to ask doubts, okay? If any doubts, even beyond these topics regarding fluid mechanics, so you can ask me in my email, or in forum you're free to ask, but regarding, if you have any doubts, you can ask me in the email. Okay, I guess that's fine.
Yes, sir.
Yeah.
Thank you, sir.
Okay. Thank you then. I guess that's all for today, because I guess today's session was not long, because these topics are very conceptual. Okay, the fluid kinetics part is very conceptual, but it's important to be clear. Okay, the difference between streamlines, streak lines, and path lines. Then when to use stream functions. What is the importance of velocity potential? What is the importance of stream functions? These concepts are very important to know, because eventually, like for different when you solve the such some advanced fluid flow problems, the use of stream functions will come out, like how it is important. Okay, so I guess you should revise through these concepts, and these are very important, and such questions are like very, what to say, very relevant for competitive exams. So since they're very conceptual and easy to make questions out of such concepts, so they usually prefer questions from these concepts. So I encourage you to read these concepts. So yeah, I guess that's all for today's class. So thank you again. See you in the next session. Okay.
Thank you, sir.
Thank you.